Hi, I'm James Cameron. I got my PhD in 2018 from the University of Washington, where my advisors were Steve Mitchell, John Palmieri, and Yulia Petsova. I'm currently a postdoc at UCLA, where my mentor is Paul Balmer. I'm interested in group cohomology and equivariant cohomology and connections with modular representation theory, and I'm particularly interested in understanding cohomology rings from a geometric point of view. I'm also interested in connections with tensor triangulated geometry and tensor triangulated geometry in general. I have some ongoing projects in group cohomology and equivariant cohomology. For example, some material involving classification results for thick subcategories of modules for Cauchy algebras for Borel constructions on G-spaces. But I want to talk right now about a project I've been working on involving homological residue fields. Given a tensor triangulated category, you can localize it at prime, but in general, there's not a notion of taking a tensor triangulated residue field. One fix for this is an object called a homological residue field. So before I describe these results, let me quickly say what a homological residue field is. So given a tensor triangulated category T, you can take this restricted Yoneda embedding of T into the TC modules, where TC modules is the abelian category of additive functors from the compact part of T to abelian groups. So since this is an abelian category, you can then quotient by a maximal Serre tensor ideal, and then the resulting object is called a homological residue field. So these were introduced by Balmer, Krause, and Stevenson, and they're useful for lots of things. For example, there's a homological spectrum built out of these homological residue fields that maps onto the tensor triangulated spectrum. And there's a nilpotence theorem for homological residue fields. So each homological residue field is controlled by an object of T in the sense that these maximal Serre tensor ideals are all of the form of the kernel of tensoring with a representable. So the question I'm interested in right now is, if there is a tensor triangulated residue field, let's call it K, how does the corresponding homological residue field compare to K? So for example, in the stable homotopy category, Morava K-theories act like residue fields, and we would like to know how do these homological residue fields for the stable homotopy category compare to Morava K-theories. So there is an answer to this question. So let me first, and it's given by this theorem of Paul Balmer and myself. So if you have a tensor triangulated residue field, let's call it K, and let's call the residue field functor F, then the associated homological residue field is comodules on modules for K for the comonad Fu. So this homological residue field, which in its definition doesn't involve K at all, is related to K in this way. And moreover, the associated object of T, whose kernel gives you the homological residue field, is a summand of the right adjoint applied to the tensor unit of K. So here's an example. For each homological residue field in the stable homotopy category, they're each given by a Morava K-theory spectrum, in the sense that the Serre tensor ideal you get is just the kernel of tensoring with the representable given by a Morava K-theory spectrum. So the Morava K-theories that we think of as being the fields in the stable homotopy category also give us the homological residue fields. There's an even stronger sense in which Morava K-theories are related to homological residue fields, which I'll just mention in this theorem of myself and Greg Stevenson, which I'll just list as these two results. There's sort of a more general framework this fits in. So in the case of the stable homotopy category, all of the homological residue fields you get are Kn star Kn comodules. So they're comodules for the coalgebra of cooperations on Morava K-theory. So they're Kn modules with some extra structure. And similarly, Each homological residue field, just for the derived category of a ring, is related to just the regular residue field for a ring. It's comodules for tor over your ring of the residue field with itself. So there's lots of questions in this area, and let me mention a few of them. The first one that comes to mind is it's natural to ask, what structure does the object of T that's associated to a homological residue field have? For example, is it always a ring object? It was a ring object in the stable homotopy category, and it's a ring object for the derived category of a ring. But it's not known if it's a ring object all the time, and it would be interesting to have a criteria for when it is, or if it happens to always be the case. So for these results I mentioned, we've had a tensor triangulated residue field, and we've been comparing the associated homological residue field. But it's natural to wonder, given a homological residue field, can you always find a genuine residue field that it comes from? Or if not, is there some sort of criteria for when a homological residue field comes from a genuine residue field? And finally, it would be interesting to have classification results for homological residue fields in other categories. I have some ongoing work involving the stable module category for a finite group, and it would be interesting to wonder about homological residue fields for equivariant spectra also.